Okay guys, I'm going to try to get all the rest of this in this part 3 video. Okay, so we're going to focus now on using what's called the quadratic formula to solve these quadratic equations. And remember how I told you those two previous methods? They will not work for all quadratic equations. In fact, I would venture to say they will not work for the majority, okay? Because most quadratic equations are not like the ones we encounter in math textbooks. Those are made up. They're engineered so that you get nice answers or nice solutions. Okay, in the real world, you would have to use the quadratic formula. So this is it right here. If you look at it, okay, it says x, the value of x will be equal to negative b plus or minus the square root of b squared minus 4 times a times c, and that's all divided by 2 times a. And remember, the a, b, and c, those are the coefficients in your quadratic function. And you also have to make sure that your quadratic equation is in standard form. It has to be equal to 0 in order for this formula to be valid. Okay. And guys, I thought about, well, do I want to do some of these by hand? And I've just decided on no. Okay. However, there is one worked out for you. If you want to look at this, you can see what they initially have to do. It's not in standard form, so if they have to subtract 7 from both sides, which puts the 7 over here and it's negative. And then you can see a is 3, b is 2, c is negative 7. And so they go on to use the formula as a template, and they input those numbers into those respective variables, a, b, and c. And then the rest of it is just a lot of simplifying. And for students, this causes them to pull out their hair because it's so easy to make a mistake. There are quite a few operations involved, and furthermore, it's easy to miscopy a number. So in a way, doing this by hand is a great exercise, an exercise in attention to detail and focus. Okay, things that we seem to be losing a lot these days. But nonetheless, you can see it is a rather lengthy process, and you've got to remember how to simplify a radical. Okay. And then you typically will get two roots. You'll get one with the positive and one with the negative. Okay, and at the very end you'll get something like this. And so in this section you're going to see, and we've already seen, some strange looking numbers. Some irrational numbers, some purely imaginary numbers, and some numbers that are both real and imaginary, like a combination of both. Okay, so be prepared for that. Now, in your homework, occasionally the software will ask you for the exact solutions, and if that were the case, this is what you would put. Okay, and occasionally it'll ask you for approximations rounded to 3 decimal places. So if you were to approximate these two numbers, this is what you would get. Okay, approximately negative 1.897 and 1.230. Okay. All right, but what we're going to do, feel free to do this by hand if you would like, but there's all kinds of quadratic calculators, and there's one right here. This is in Blackboard, by the way. Okay. All you have to input is the values for A, B, and C, and the software will actually compute the quadratic formula, okay, just like it did here. And so that's what I'm going to rely on, okay, just to kind of get through this section quicker. All right. Example 5, it says use the quadratic formula to find exact solutions. Real quick, just let me point out, the quadratic formula will work for all of those that we've previously done. as long as you put them in standard form and assign the right values for A, B, and C. If there's a variable missing, that corresponding coefficient is 0. Okay, you have to know that. All right, well, let's look at example 5 here. I'm looking at this and I'm noticing it's not in standard form because it's not set equal to 0. Well, I can put it in standard form if I add 5 to both sides, okay, because that's a -5 on the right hand side, and then it will be equal to 0. Alright, so now it's in standard form, and so now you can see that A is equal to 2, B is equal to 2, and C is equal to 5, and you have to pay attention to the signs as well. The signs go with the numbers. And guys, I'm going to write that we're going to be using the calculator. Okay. Alright, so the value of my coefficients are 2, 2, and 5. Okay, you do that, you hit calculate. And the nice thing about this particular website is that it'll show you all the steps, for one thing, kind of take you through it step by step and eventually arrive to this. Okay, so notice there's two values here. There's -1/2 plus 3/2 I, and then the second solution is -1/2 minus 3/2 I. Okay, now how are you going to express this? Because sometimes, well, first let me write it. X is equal to -1/2 plus or minus 3/2 I. Okay. Sometimes the software will allow, there's a plus minus key, so you could just type this in. Other times you might have to separate it like this. Say X is equal to -1/2 plus, you have to write that as a fraction, 3/2, and put the I out beside it. When you do that, you're writing it in this form, A plus BI. And this A and B have nothing to do with the A and B that came from the quadratic function or equation. This is the form of a complex number. That's what this is. A complex number has both a real component, A, and it also has a purely imaginary component, B. In fact, all of the real numbers are complex numbers such that B is 0. That's why the imaginary piece never shows up. Okay. So anyway, just be aware of that. And then I would put a comma, and then the other solution would be -1/2 minus 3/2 I. Okay. Alright, so like I said, you're going to see some different numbers that you've maybe never seen before. But these numbers, guys, would be very common to, well, a mathematician, obviously, or an engineer. These numbers, these complex numbers, are nice because they're sort of constructed from two pieces, a real component and an imaginary component. And so lots of times when you're describing processes like in electromagnetism and stuff like that, in which there are two physical processes occurring, then these complex numbers become very convenient to represent those processes. Okay. All right, but in any case, these would be the solutions to this equation. Okay. They're not just real numbers. They're not real numbers like we're used to. All right, so we've sort of talked about zeros before. I told you that the zero of a function, more specifically a quadratic function, is just a value of x that makes it equal 0. Okay, so all of these equations that we've solved thus far, they were all equal to 0. So we were finding the zeros of those corresponding quadratic functions. Okay, and more generally, guys, for any sort of function, a 0 is just a value of x that makes the function give you an output of 0. And that's what this says right here. It says c is a 0, the number c is a 0 of f of the function if you can plug it into the function and you get 0. Okay? Now remember, if the function gives you an output of 0, the output is the same thing as your y coordinate. Okay, so you could represent this using an ordered pair. C is the input, or C is the 0. It's the value of x such that we get a 0 out of the function. Or in other words, it's the value of x such that y is 0. And what graphically this means is it'll be this form right here. Okay, the y coordinate will always be 0, and the x coordinate is the 0 of the function. Okay, so this is an x-intercept. Any ordered pair that has this form in which the y coordinate is 0 will be on the x-axis. So what we're saying here is when we solve a quadratic equation in standard form and we find those values of x, those are the values of x where the function crosses the x-axis or intercepts it. I'll show you an example. Let's go way back up here. Let's get one that had nice solutions. How about this one? This one right here. X squared minus 8x minus 20. Let's go to Desmos. I'm going to graph this. I'm going to put y equals x squared minus 8x, I think, minus 20, right? 20, okay. Now I'm zoomed out from another class, but look at this. Where does this, of course it's a parabola. You can see it's really steep though, right? It's been horizontally compressed or stretched vertically. But where does it cross the x-axis? Well, it crosses right here. Notice this point, the y is 0, and what's the x? Negative 2. And over here, the y is 0, and x is 10. Let's look back at the notes. What are the values that we got? Negative 2 and 10. So all of this is tied together. When you solve a quadratic equation that's set equal to 0, the zeros are like the x-intercepts. It's where the function crosses the x-axis. Okay, so graphing is a legitimate way to try to solve a quadratic equation. The problem is, what if it crosses the x-axis and you can't really tell what number it crosses at? Then the graphing method kind of breaks down. You need to use the algebraic method like we've seen. Okay. Alright, so start thinking about zeros as not only being solutions, but also corresponding to the x-intercepts where the function crosses the x-axis. Here's another example. Here's the quadratic equation in standard form. Okay. I'm looking at this and I'm trying to think, can it be factored? And yes, it can. You could solve this one by factoring if you wanted. But you could also solve it using the quadratic formula. And if you did, the values of x that you would get are right here. Where it crosses the x-axis, you would get a -1. That would be one of them. The other one would be 3/2, which is the same as 1.5. Okay. So I hope that this is making sense. In fact, why don't we try this using the quadratic formula real quick. A is 2, B would be a -1, and C would be -3. So 2, -1, and -3. 2, -1, and -3. Let's calculate. Look at what we get. -1 and 3/2. Okay. So the zeros of a function are the solutions when you set the function equal to 0, and they're also where the function crosses the x-axis. All right, so we try to really here we go. Okay. Yeah, so try to really think about that and try to commit that to memory. Try to understand that conceptually, because we're going to be going back to that over and over again. All of Chapter 8, which is Module 3, is about finding zeros of functions. We're not just going to be focusing on quadratic functions. Okay, let's look at example 6 here. It says use the graph of f of x. So we've got two different functions here. You can see they're both quadratic because these are both parabolas. To find the x-intercepts of the graph and the zeros of the function. Okay, so if I'm looking at this one right here on the left, the x-intercepts are going to be actual ordered pairs, because that's what an x-intercept is. It's a point. Okay, so this is an x-intercept and this one is an x-intercept. So what are the coordinates of those points? Well, the first one looks to be -1, 0, and the second one looks to be 2, 0. Okay. Now, as far as the zeros of this function, the zeros are just the x values. So you just put x is equal to -1 and 2. In other words, if we knew what the function was and we plugged in either -1 or 2, the function would give us an output, or a y, of 0. Okay. Similarly over here, this one's interesting because you're looking for the x-intercept. Where's the point where this function crosses the x-axis? Well, it never actually crosses, but it does touch, and it touches right here. So it only has one x-intercept, and it's the ordered pair 1, 0, with a point located at 1, 0. And consequently, guys, it only has one 0, and that is x equals 1. Okay, so this particular quadratic function, if you knew what it was and you set it equal to 0 and solved the equation, you would only have one solution. Remember how I told you previously that most quadratic equations will have two solutions, but sometimes they only have one. Well, this would be an example. All right, we're doing pretty good. So we'll do these last ones using the quadratic formula. Example 7, it says find the zeros of this function. Well, all that means is you're going to take that function, you're going to set it equal to 0, and you're going to solve it for b. Okay, so you're solving a quadratic equation again. And if you're using the quadratic formula, your coefficients, a is going to be an understood 1. This b has no relation to the fact that the independent variable here is b. Okay, that's just a coincidence. B is 14 and C is 48. This one is one that you could solve by factoring as well, but I'm going to use the quadratic formula solver. So 1, 14, and 48. We get nice numbers. If they're factorable, guys, you're going to get nice numbers for your solutions. -6 and -8. Okay. So we'll say that b is equal to -8 and -6. These are the zeros of that function. If you graph this function, it'll cross the x-axis at -8 and -6. Let's go ahead and see this. Just to be thorough. b, I think this will let you use the variable b instead of x. B squared plus 14b plus, was it 40? No, it wasn't, because it's, go back and look, it's 48. Whoops, 48. Let's zoom in here. Where does it cross the x-axis? When x is -8 and when x is -6. Okay. All right. Let's do a couple more. This one, it says find the zeros of the function. So technically, again, you set the function equal to 0. That gives you a quadratic equation, and then you solve that quadratic equation. Okay. Now I can look at this one and tell you it is not factorable. A is going to be 1, B is -2, and C is -4. Okay, so we're going to use the calculator again. Oh, I forgot what they were. 1, -2, and -4. 1, -2, and -4. Alright, so look, it gives us the decimal approximations, but it also gives us the exact answers, or the exact numbers. And those are 1 plus square root of 5 and 1 minus square root of 5. Okay, so that's what I'm going to put in my notes. X is equal to 1 plus the square root of 5, and so you separate them with a comma, 1 minus the square root of 5. Or if the plus and minus key is in there, you can say 1 plus or minus the square root of 5. I'll say a couple things about this one. These two solutions are irrational numbers. They're on the x-axis, so they're not imaginary. But they're going to, if you were to graph this function, it'll cross the x-axis close to these two decimals. These are decimal approximations. So close to about 3.2 and then -1.2. Okay, but see, if you were graphing and trying to see where they cross by looking at the graph, you would never know they're crossing at 1 plus square root of 5 or 1 minus square root of 5. So that's why the graphical approach to solving quadratic equations is not robust. You've got to do it algebraically. And then down here it asks for the equivalent decimals. Okay, so we can go ahead and add those in. Usually we want to round them to 3 decimal places, so this would be 3.236, the first one. 3.236, and then the second one would be -1.236. Okay. Also pay attention, because the software might ask you to input the zeros in ascending order. So if that were the case, I would put the smaller 0 first and the larger 0 second. Okay. Alright, well, we're doing good. We're going to look at one last. Same thing here. Okay. And I can tell you by looking at this one's not factorable either. So if we want to find its zeros, we're going to set it equal to 0, and we're going to solve this equation using the quadratic formula. A is 4, B is a -1, and C is 9. Okay, so we're using the quadratic formula. We're just not having to do all the calculations. So 4, negative 1, and 9. Alright, now look what we come up with here. This one is very strange looking, isn't it? 1/8 plus or minus the square root of 143 over 8 times I. Okay. Notice this calculator likes to put the I up there in the numerator. The software in your homework doesn't want the I up there. It wants it out beside or behind, kind of like the way it's written here in decimal form. Okay. So when I write this in my notes, I'm going to write x is equal to 1/8, I'm going to separate them, plus the square root of 143 over 8. Now put the I out beside it. When you do that, you are writing it in this form right here. A plus b I. And then the second solution, or 0 rather, is 1/8 minus the square root of 143 over 8 times I. Okay, so this is a complex number. Both of these are complex zeros that contain both a real and an imaginary component. Okay. Now lastly, what I want to do is I'm going to graph this one for you. So 4x squared minus x plus 9. Okay. Alright, well where is it? Okay, well I'm going to have to zoom out to see it. There it is. There's the parabola, okay, which is consistent with the fact that this is a quadratic function. But you may be wondering, like, well, we just came up with 2 zeros, or 2 solutions. Why isn't it crossing the x-axis at those 2 values? Well, look at these values. They're not purely real numbers, okay? These numbers don't exist on the x-axis. You would have to have a complex axis, or an x-axis that represented complex numbers. And they do that some in math, okay? In fact, sometimes if you were ever to go on and study math at a deeper level, you can graph these complex numbers and you can do it by letting the x-axis represent the real piece and let the y-axis represent the complex piece, or the imaginary piece. Okay. But anyway, what I was wanting you to see was the fact that because of the nature of these zeros, this particular quadratic function doesn't cross the x-axis. It doesn't mean it doesn't have zeros. It's just that the zeros have imaginary components with them. Okay. Alright guys, well I think I have more or less exhausted this. Okay. I may try to put a couple other videos on factoring in there for you to watch if you want, supplementary videos. But you can solve all of those quadratic equations, or find the zeros of the quadratic function by using the quadratic formula. Okay, so, but you do need to know how to factor some, because we're gonna be factoring some more later on, and factoring will be a crucial process for some of the work that we do later. So, all right, well I'm going to stop there on 7.4, and I believe we go to 4.8 next.